He was like my second father.
Yes, yes,
My,
yes, absolutely. He used to treat you like that.
Uh, Good afternoon, sir. Good afternoon, Pankaj Bharatia, sir.
Good
And
afternoon.
welcome all the participants. Thank you for joining the present session on international best practices being supported by EPRI. They are helping us out with all the speakers in the session. First of all, I would like to welcome our session chair for this session, Mr. Pankaj Bharatia, sir. He has more than 35 to 40 years of experience in thermal power plants. He retired as General Manager from Senpeep NTPC Limited. Sir, request you to please begin the session. Thank you.
Okay. Thank you, Mr. Mehul. It is my privilege to be among you, and the session being on the latest technological developments in the power sector. And first of all, let me welcome our learned guest, Mr. Stephen Storm, who has been to our Indian power plants quite extensively and has done in and out studies and recommendations and got the implementations supervised and reconfirmed. So he has got the first hands-on, feel about our boilers and plants. And I would also like to welcome Mr. Kafi, who is going to talk on O&M best practices, and Mr. Justin Three Bolts and Jeong Kim, then Dr. Prayag Parekh. So on this session, we'll have, it's a great opportunity that we are able to have so many of, luminaries from EPRI who will be delivering their talk on various technological developments and issues. Technology is the key driver for meeting the challenges of the thermal power plants generation and environmental concerns, as well as integration with the renewables, which is the talk of the day today. A lot of research is going on around the world. We are fortunate to have with us the speakers from the world's leading institute, which is involved in the research and deployment of technologies in the power sector. In fact, we at NTPC were fortunate to have been involved with the EPRI in developing the systems and practices and deployment of the technologies at our plants and sharing the learnings with other Indian power plant people. First of all, I'd like to invite Mr. Stephen Storm, who is going to talk on the flexible operation. The flexible operation being a in thing, we need to understand the boiler reliability considerations and adopt appropriate strategies for boiler operation. So, first of all, I'd like to invite Mr. Stephen Storm to talk on this subject. Mr. Stephen Storm, please. Stephen, I think you're on mute.
Yeah, sorry, Pankaj. If somebody can pass me the ball, I'll be happy to share my screen. I think Dwayne has it right now.
Okay, okay. Mehul, can you just organize?
Dwayne, can you pass me the presenter ball, please?
I'm just doing that, sir.
Okay, thank you.
I think
There
you
we
would have
are.
got. Is the share button live for you? Okay.
Yes. Yes, thank you. Thank
Yeah.
you. Okay, good afternoon, everybody. I'm very happy to be here with you. Are you able to see my screen now and hear me okay?
Yes, Mr. Storm.
Very good, very good. So I'm going to speak on the subject of boiler reliability considerations under flexible operations. This boiler tube failures continue to be a leading cause for availability losses in fossil plants worldwide. So I think this is an important subject to India, especially as you continue to undergo increased levels of EPRI integration. So I'm excited to be able to present. I'm excited to share this panel with some of my associates who I think are going to add some additional perspectives on operations, maintenance, and technology best practices. So let me first get started and kind of share with you, the fact I think it's important to begin with emphasizing that energy markets and the demands from the energy market are really what drives the operating modes at thermal power plants. So when you take that into consideration, some food for thought is to consider that grid stability is truly at the mercy of boiler reliability. As I started out saying, some of the leading causes of boiler reliability across the world are boiler tube losses. So I think it's important to understand, how that's driven by the energy markets, how flexibility relates back to boiler reliability, and how you manage the variable renewable energy that gets integrated into the grid. As you can see in this table, in the US, we have a lot of gas generation, a lot of combined cycle, a lot of simple cycle. This is something I know India does not have a large portfolio mix of. So when you're looking at the energy mix in the portfolio, and if you do not have these fast start gas turbines, hydroelectric or reciprocating internal combustion engines to basically assure the grid is stable to be able to meet those 1 to 4 hour lead times for startups and shutdowns, to be able to operate with extremely high ramp rates up and down, then we really put a lot of pressure on the fossil plants and the conventional coal plants to be able to prevent instabilities in the power grid, and how you manage those assets is very important. The next thing I want to talk about is again, I mentioned that boiler tube failures are a leading cause for plant availability losses in fossil plants, but the overall reliability of those plants is really influenced negatively by the number of startups and shutdowns. And a lot of those startups and shutdowns and the failure mechanisms that arise from boiler performance are at the mercy of plant operators. And so some of the common operational challenges include how you manage those high ramp rates, poor control of the temperatures, poor control of drum levels, pressure and temperature control and whatnot. And all the damage that you accumulate on a large utility boiler is accumulative. Yet to find any unit that was self-healing. So I think it's important to understand that all this damage is accumulative, and it's important to understand that you have to have a comprehensive mitigating strategy to prevent premature failures of major components. So as you're going across the load range and you look at the demands on those conventional coal plants for dispatchable generation, you got to be able to meet those grid stability demands by being available, being flexible, and that flexibility might not be online operation. That might not be how quick you can ramp up or ramp down or what your minimum turn down is, but it's also your availability after you come out of a short-term layup or an extended wet layup or a dry layup. But for these different modes of operations, there's different requirements for the plant staff. And I think it's important that you understand that each one of these modes of operations comes with a defense strategy that includes O&M activities that are critical for ensuring boiler reliability. So when you look at boiler reliability, as I've spent the majority of my career doing, boiler performance optimization plays a very large role. Whether you're talking about load following, minimum load, two shifting, or even in a layup scenario, you need to understand what that mode of operation has on the performance, as well as potential material degradation. So on the right-hand side of this slide, I've shown some of the very common issues that we've seen from different modes of operation. So for example, when you look at minimum load or reduced load operations, there can be issues with circulation, superheat and reheat, overheat, economizer steaming, flash, layout, or so forth. And then when we get into situations like two shifting or increased startups or shutdowns, you have more vulnerability to thermal fatigue or operator error. And I think Dwayne's presentation, which follows mine, will be very complementary to how you take that into consideration. So pulverized coal combustion, as anybody that knows me knows that that's near and dear to my heart. And all utility boilers, pulverized coal-fired units, which are predominant in India for generation, are fixed with a limited amount of furnace residence time for combustion to take place, typically less than 1 to 2 seconds at a time. And within a microsecond, you release the volatility in the coal. And as anyone in India knows, that there's very little volatile to begin with. So you've got to get combustion right. Combustion is a major influencer on heat transfer optimization, and it plays a big role in operational flexibility. So, you know, as you drop load and you deal with low volatile, high ash coals, forced ignition points and how you modulate mills into the configuration and how you control excess airflow and issues such as air and leakage are very important. They have a very much of a negative influence on combustion, and it can not only impact the boiler, but that can impact the turbine side.
Mr. Storm, we are unable to hear you.
Used for deposits and waterside chemistry issues to where these can influence corrosion, fatigue, and other mechanisms that may show up in the system. And then we have the issue of how do you manage heat rate and how do you manage the boiler losses and the heat that's rejected back to the coolant towers, and what influence does that heat rate have on your firing rates to make sure that you're even in the mix, dispatchable and justifiable to be able to meet those grid demands and generate megawatts so that you can stay economically viable in the future going forward. So management typically one of the top areas for control improvements. It's a very important area. Regarding pressure and temperature control, combustion and boiler performance, once again, play a big role in that. The controls are very important, but there's also a lot of subsystems. When you look at the air systems, the gas systems, the fuel systems, you know, and how you manage those different controls that modulate those different subsystems. And depending on the mechanical integrity of dampers and burners and pulverizers and how good of a job that the firing system is doing for ensuring that we optimize lower furnace heat transfer, is going to have a big influence on the magnitude of those temperature and pressure swings, which are top drivers in regards to the life expectancy of thick-walled pressure vessels. You know, we can see issues with boiler terminal tubes that tend to suffer from thermal and pressure-induced fatigue issues. And those issues are again related back to combustion. They can be related back to human error, and it goes hand in hand with operational best practices and how you manage the procedures as you go up and down and load. One of the top areas, I know a lot of the Indian power plants, because the coal quality, have struggled to operate with less than 50% load. I know there have been some burner studies and areas to where you've been able to prove for a short amount of time the ability to go down to 35, 45% MCR in my understanding. but due to shear bar wear and burner degradation over time, the sustainability of reduced low load operation is going to continue to be a challenge in India. So, it's important to understand, how you manage that heat release. When you operate in that 0 to 30% load range, this is what I sometimes call the valley of the shadow of death. We have reduced pressures, we have reduced differentials on the superheat and reheat, and we find ourselves more susceptible to circulation issues or any issues that you might have with exfoliation in your U-bends or your superheat and your reheat because of overheat scenarios or flame impingement or heat flux variations in the furnace walls can result in a short-term failure mechanism. And of course, those short-term overheat situations can turn into long-term overheat or failure mechanisms that don't show up for many months down the road. A lot of those failure mechanisms remain latent for a long period of time. So although you might find yourself flexible for a year or two, in many cases, what we've seen with large utility boilers is that over the first 2-3 years with operating with high ramp rates or increased levels of or reduced levels of minimum load operation, you may not see DNB failures or overheat scenario failure mechanisms show up for some time. So it's important to keep a focus on those potential failure mechanisms. That being said, I've always been a proponent of the inputs and making sure that when you are pursuing a combustion or a boiler performance preservation program, you need to take into account the firing system, and the firing system being the pulverizers, the fuel lines, the distribution, how you manage those excess O2 curves, how good of a job you're doing with representative O2 measurement at the back end. And that's extremely important at low load operation and making sure that we meet those NFPA requirements to minimize the possibilities of explosions or to minimize the possibilities of ash layout and or issues that can not only have a negative impact on boiler reliability, but also environmental controls equipment on the back end. With large utility boilers cycling more often in India, and when you have domestic fuels with 40% ash coal, you already have issues with air and leak with accelerated flash erosion on major components of refractory and penthouse seals, expansion joints, and so forth. But as you cycle on and off, and the boiler modulates as much as 6 to 12 inches or a half a meter up and down as you take the units on and off, you're going to see more issues with the possibility of air and leakage. And so ensuring furnace stoichiometry is where it needs to be, ensuring your O2 measurements are representative, and doing periodic inspections to ensure that you have gas tight furnaces, convection passes, and even everything downstream of the ESPs, going to the ESPs to ID fans, because if you run out of ID fan capacity and then you do drive back up to low load, then the only thing the operator could do is operate with less O2 or reduced load. And that creates challenges with meeting that load range going forward. So I think the best way to evaluate that as a best practice is to do a periodic boiler performance evaluation to where you're monitoring the heat transfer on the unit. You understand when there's a shift in performance. You do periodic testing and requirements. You understand the different materials as you go from the furnace walls to the superheat, the reheat. As you know, you're going to have material changes. And those different material changes are going to vary for your castings, your components, your boiler tubes, your refractory, the metal casings, your access doors. You're going to have different expansion rates. You're going to have different challenges for different materials. So understanding what those metallurgical limitations are, understanding what your performance is, where your heat absorption path is, and then also understanding what's going on with chemistry. Understanding when you have chemistry upsets and you have tube deposition internally on the tubes, it's important to understand that startup overheating of those boiler tube components can be related back to the oxides that are inside a superheat and reheat tube, because they expand at different rates than the material itself, and so that can really drive failure mechanisms on those major components. Starting up and shutting down more. If you have an event to where you're in a peak of summer or peak of winter, India probably has more peaks in the summer than the winters because they're much more mild than some of the climates in other parts of the world. But the more startups and shutdowns that you do, if the operator runs the ID fans for an extended period of time, or if we start pulling off hatches on the boiler after you shut down and you force cool the unit, you can run into situations to where you really drive condensate buildup that can create a water plug in a superheat or a reheat tube. And then when you come to start back up, what happens is you can not only start up and have poor circulation and exceed the metallurgical limitation of that component because your FEGT is higher than the design of the tube material. But if you have an issue to where you have condensate buildup and you don't monitor that FEGT and you don't control those gas temperatures until you evaporate off that condensate in those U-bends, then you're going to result into a very short-term failure mechanism. So it's important to have gas temperature measurements on the unit, as well as understanding what's going on with those components. We've seen a number of issues with cyclic operation to where you can have these water migration events, not only on boiler components, but also on turbine water induction. But looking at boiler components only in this presentation, it's important to understand that these rapid temperature cycles can lead to high strain ranges in borehole surfaces near the mid-wall thickness of headers, as I'm showing here. And then as you have more startups and shutdowns, those higher strain ranges can result closer to the internal surface of the header itself. But this is just an example on the right of a graph to where you had a water-cooled spacer tube, and then at startup and shutdown, you're getting these slugs of water from these saturation events to where you have water quenching of that borehole, and then that ultimately is going to lead to cracking. And then when you're looking at life, and John and Justin may have some comments on long-term maintenance activities, but when you're trying to manage uncertainty and you've got units that are 30 or 40 years in age, there's a lot of uncertainty about the end of life of the units and what kind of damage may be done to major boiler components. In the US, it's not uncommon to see if you have to do a major header replacement, it might be anywhere from $5 to $20 million US dollars. And if you've got a unit that is only going to be operational, it's already been through 25, 30 years of the original planned life, and it's going to only operate for 3 or 4 or more years, that may be very difficult to justify the repair cost for that failure mechanism. So it's important to understand these failures, what are all the precursors to those potential failure mechanisms, and what are all the variables that relate back to it. So I can't stress enough the importance of having representative thermocouples across the system. I can't stress enough the importance of optimizing combustion and boiler performance and having good pressure management on the units. But all these different systems align to control the steam temperatures. On the subcritical units, these are more prone to having issues with drum level control and catastrophic damage when you drop down to reduce loads, or if you have more startups and shutdowns, you can have issues with shrinking and swelling of the water levels due to heat flux and what's going on in the combustion process. So as you continue to drive closer to 50% load or even reduced load operations, it's important to understand what's going on from a circulation standpoint and how good of a job that your combustion is in the lower furnace by doing visual observations, doing periodic testing, and doing those prerequisites to be able to mitigate those potential failure mechanisms. So when you look at something very common, when you get down below 30% MCR, we've seen a lot of issues with departure for nucleate boiling, to where you have steam film formation. that on top of any potential scale or deposition that you have from water chemistry upsets, you can also have a temperature differential from the film formation from having a high heat flux region to where you have DNB. So it's important to understand that a lot of those failure mechanisms are related back to combustion. And then when you look at the deposits in the tube, I'll just give an example here on a subcritical unit where you might be designed for 360C on the inside of the boiler tube. But if you have significant amount of scale on the inside of the boiler tube, that can create a temperature differential of close to 150 degrees C, to where now on the exterior of the tube surface, because you don't have the steam cooling or the saturated steam cooling on that subcritical boiler, you might start hitting 980 F or 527 degrees C on that tube wall. And if that's carbon steel tube, that's going to result into a short-term failure after a very short amount of time. So it's very, very important to understand those heat fluxes. And then it's also very important to ensure that you have optimal stoichiometry at the furnace exit. Anybody that's ever done a high velocity thermocouple probe test, or where you use a water cooled probe, you check the O2, you check the temperature profiles in the boiler, can attest that it's not a fun test, but it's certainly a best practice that should be considered annually or semi-annually to ensure that you've got the proper amounts of oxygen and that your lower furnace heat absorption is where it needs to be. And then in regards to real-time management, integration of infrared or acoustic pyrometer systems is well warranted, so that you understand any potential change in the performance over time. As you do change those temperature, pressure in the boiler, and if you operate, and if you say you drive, don't absorb the heat in the lower furnace due to air and leakage or flame stability issues, or just poor absorption in the lower furnace, which relates back to combustion, this can drive those furnace exit gas temperatures up 150, 200 degrees C beyond the temperature limitation of the ash fusion temperature. And then with high ash domestic Indian coals, it's also important to understand that there's an exponential impact on the velocity gradients of the fly ash accelerated erosion mechanism that relates back to those temperatures, because you didn't absorb the heat. So not only do you have to absorb more heat in the superheat and reheat to be able to meet the turbine inlet demands for steam temperature and pressure, but you're also going to find yourself with accelerated erosion, accelerated plugging, and increased heat absorption on the superheat and reheat, which is going to shorten the life expectancy of those major components in the upper furnace. As that boiler goes up and down with cycles, when the unit comes on and off, the boiler relies on adequate supports and expansion joints to be able to handle that significant amount of movement. The boiler needs to be able to articulate around buck stays. Any attachment points that are fixed or inability to modulate is going to exacerbate issues with fretting and rubbing and tears and things that result in boiler tube failures, like I got illustrated at the bottom left. But this can also relate back to exacerbating corrosion fatigue at attachment points, to where you also, have issues with a boiler that's, say, over 30 years of time, and it's all of a sudden cycling more so at low load operation. So I always look at the firing system as the heart of a coal-fired unit, but I look at the air system and the air heaters as kind of the lungs of the unit, ensuring that we have good differentials, balanced pressure drops, uniform gas flows and temperatures are not only important for boiler reliability, but it's also important for optimization of your electrostatic precipitators, ensuring that we have adequate velocities to be able to sustain those ash particles and not have issues with high ash coals like we've seen in India, to where you have deposition in localized areas, whether that be in the upper furnace, the convection pass, or in the horizontal ducts that are leaving the boiler, because ultimately that's going to impact gas distribution in and out of the unit from left to right side, and that's going to ultimately impact the dynamics of what's going on in the combustion process on the front end. So I briefly mentioned.
Mr. Stephen, could you now try to wrap it?
I can wrap it up. So I talked about corrosion fatigue earlier. Flow accelerated corrosion is something that modulates with low load. We find ourselves more susceptible when we drop down to that 150, 180 degrees C range. And then cycle chemistry, how you manage it online and offload is very important. So I'll wrap it up, Pankaj, with saying that under these different modes of operation, there's different requirements for each one of those modes. There's a lot of different subsystems that need to be taken into account. And it's very important to have defense mechanisms for aligning your people, process, and technologies. And I know in Program 223, this is a key focal point for us. And so anybody interested in learning more, please reach out to myself or Paul Pickering, our India representative. Happy to share more separately. Thanks, Pankaj.
Thank you, Mr. Stephen. It has been a very comprehensive, assessment of the Indian boilers, which you definitely have done it hands-on. And it is a good learning from the perspective of the flexible operation. And as you rightly say, that the people, process, and technology all have to put together to, address this issue. And the points which you have raised regarding, the controls and the, the ramp-up rates and the metallurgy and the operation optimization and the tracking of the temperatures, metal temperatures, gas temperatures, and the fire completion temperature. So these are all the major issues which we need to monitor in order to be confident about, the lesser adverse effects of the flexible operation. Thank you so much.
Thanks, Pankaj.
Thank you. So now I would like to invite Mr. Cappy, who is going to talk on the O&M best practices. Please, sir.
Thank you, Pankaj. Happy to talk to you guys today. If you could pass the presenter ball over to me, I'd be very happy with that.
Mehul.
There we go. Thank you. We're not going to talk about waterfalls. There we go. Thanks everyone for allowing us to talk to you guys today. I want to talk about plant success with utility-focused human performance. So we're going to talk more about organizational operational excellence in the power plants. Like Stephen talked about, some of the issues are operator error, but it's really not so much on the end user operator as it is on other opportunities that we have. So if you're talking about human performance, it's an interconnected system. A lot of people don't understand that. But if you look at your end user there, the power plant operator, he's affected by a lot of things: people, programs, processes, the work environment, organization, and even the equipment. And all of those things are connected together, and all of those things interact with each other consistently. So you have a lot of multiple factors changing instantaneously that affect what your end user does. So it's a very interconnected system, and a lot of people don't understand that. The end user is going to make mistakes based on what decisions he makes based on all of those things that are impacting him instantaneously. A lot of latent conditions exist in these human performance conditions, and that's really what we're going to talk about. If you look at industrial event root cause statistics, where people have figured out when events happen, 80% of it is human error. I know Stephen's real passionate about the boiler, but equipment failures is really 20%. Most of these events are caused by human error. But when you look into the human error, you can't stop just saying it's a human error. You have to look at it, break that down into smaller details. And when you look at the human error, then it actually evolves into this. You have latent organizational weaknesses. So your programs, your processes, those are the issues that are actually causing problems with your units. And then the individual human error is a very small percentage of that. So we really need to focus on the organization. The programs, the processes that you have in place are hugely important, because that's where the latent organizational weaknesses exist. And there's all kinds of examples. Our industry is not the only one. When you start looking at the latent organizational weaknesses, you're going to start looking at your process and programs and your organization. In the U.S., we've had some big events of our own. The Space Challenger, the Challenger explosion was a latent organizational weakness. Russia, the Chernobyl nuclear plant, obviously a latent organizational weakness. And then we've been, this is a combined cycle plant that exploded during commissioning in Connecticut, the clean energy complex, due to a poor process on your steam blows for your steam piping to clear the piping out. They were using natural gas for the steam blows just due to the environmental conditions and how they had it set up, that there was a pocket of natural gas that existed during the steam blow. It found an ignition source and exploded. And you can see the damage there. Thankfully, they went ahead and repaired that and put the unit on service. And despite all of that damage, there weren't any deaths. So that was very fortunate. So my program looks at a lot of latent organizational weakness areas. Stephen talked about procedures. That's very important. That's one of the key opportunities. How you use those procedures, the use and compliance. We find out when we do assessments across the world, we're not as good at that as we should be. Hazardous energy control, like lockout, tagout. Making your operator rounds, like Stephen was talking about, the inspections of the equipment, really important. And then we've moved into the technology, DCS. So our DCS alarm management, we find everywhere we go around the world is poor. That's well beyond what a human can actually perform. We'll talk about that. And then just a look at the graphics. These graphics are great if you're playing a video game. They're horrible if you're trying to run a power plant. And we see these graphics everywhere. I was at a plant doing an assessment last week. They had graphics that look just like this. It's very, very poor for a human. And then there was about 10%, 6 to 16% for individuals who make mistakes. So there's some tools there that we could help with those also. And we try to help the industry be better with those issues with the individuals. So the first one we talk about was the procedures. So there's a lot of errors that are in procedures because we don't train people how to write procedures. We just expect them to understand that. We train them to run a power plant, but for some reason we think everybody is born with the ability to write a procedure when they are not, and they need to be trained. Here's some examples of plant procedures when we provide a training program to plants so they can write procedures better. We ask them to send us their procedures. And here's some examples of errors that created by people who aren't good writers. They don't understand they're not good writers, but it's nevertheless, these are the issues they cause. If you look at the time and initial on these, great tools for placekeeping when you're going through a procedure, but they're on the wrong side for a human. How do we work? We read left to right. So it would be better for the time and initial to be on the right-hand side instead of the left. And the reason being, for example, the person is doing step 2. As soon as he gets to step 2, he's going to put a time and initial it, and then he's going to read the step. And about halfway through the step, he gets interrupted. He goes away, has to do something for 10 or 15 minutes, and when he comes back, he forgets where he was, so he looks at his placekeeping, right? Well, number 2 is signed off. We haven't done it, but it's signed off. So now he thinks, well, I'll start at number 3. So the placekeeping is wrong. It needs to be on the right-hand side. That way, you don't put the time and the initial until you complete the step. That's just natural human performance. But writers aren't trained in that as well, and they make those kind of mistakes. A lot of other ones on this thing, all applicable. Well, who decides that's applicable? That'll be an end user. You have to, and is all applicable the same for every individual? It's not. What is properly? Again, one of those words that it's different for every individual. You have to state what properly is. You can't use big generic terms like that. On number 7 down here, all substations. How many is all? Is that 5, 10, 15? Your end user needs to know that. So what you're doing here with a poor writer is you're setting up your end users to make mistakes. And there's more words like that: instruct, notify, verify. All of those words mean different things to different people because of their backgrounds and education levels. So you have to establish what those terms mean. This one is a great one. This is on feed water. is responsible for the operating staff to ensure all the systems, all the equipment needed is in service. Well, what is that, right? That one little word, that one little step requires a large amount of action that's not mentioned in here. It tells your end users what to do, but it doesn't tell them how to do it. So that's where they start making the mistakes. They understand what they need to do, and they're going to go out there and do the best they can, but they're not going to be successful because that is so massive a undertaking for them, and they're trying to do it from their memory. They're not going to be successful. And we got a lot of statements in this area that way. Verify a water panel set up for proper analysis. Make sure all the equipment is prepared for service. All instrumentation's ready. Again, these are big, huge statements, and there's no guidance on how to do them. So it's inevitable that they're going to make a mistake in the end. And that's because of the poor writing, not because of the end user is not good. Is not a good person or a good operator. A lot of those, and we see this over and over again in procedures around the world. Is the person who writes it writes it based on excuse me, he writes it based on his skill level, and that may be very high, but the end user is just probably a newly qualified person, doesn't have that skill level, and he can't complete that step successfully without more information. Then if you even have a good procedure, if you don't teach people how to use it, they'll still make mistakes. All our personnel need to be trained because they don't have experience with procedures. Procedures is not something they normally get taught in school, right? You don't learn it in school. You don't learn it through universities. Typically, procedures are not used there. Our industry uses them quite a bit. So we have to teach people how to use procedures correctly. We recommend that you have different usage levels for procedures, and that's based on the risk, complexity, and how often you do it. So we have a high level called continuous or in hand. That's a high risk job. That's very complex, and you don't do it very often. Those are three categories that would put you in a continuous use, which means I read the step, I do the step, then I go to the next step, and I sign it off. Very, very, it's a very detailed checklist where I perform it in a very detailed sequence, because if I make a mistake, it's very hazardous to my plant, and I can't, usually it's irreversible. I can't back up from it. Then the next level down is called reference. That's, things that we do more often, a little less complex, not as high risk. We want the procedure with us. We may look through the whole page and say, here's what I need to do now, and we go do it. Then we stick the procedure in our pocket, we go do those steps, we come back, pull it out, look at the whole next page, go do that. That's reference. And then information is like procedures for how to fill out maybe your timesheet, or how to do overtime callouts. It's procedures and processes that don't actually touch plant equipment. So if it doesn't touch plant equipment, it's not a high risk to my plant. So that's why we call it information. But they're still valuable and need to be there. How to use PPE, those kind of things are information type procedures. Prerequisites, a lot of people get in trouble because they'll get their prerequisites for doing a process in place. Then it's break time, so they go to break and they come back and they don't verify that those prerequisites still exist. So they start right back in with the procedure and something happens. And that's because we all know in power plants, those change very rapidly. So while I'm gone on a break, those conditions could change. And if I don't come back and change and verify that they still exist, and now I start my procedure without that verification, I can have a problem. And we've had multiple events in the US I can point to where we did not do that and cost millions of dollars to repair just because we skipped that step. You need to tell your end users what to do when things happen, like when they get interrupted, what should you do? You need to tell people if they get to a step and you can't perform it as it's written, what do you need to do? What happens when you're doing a task and a casualty occurs? What do you need to do? And then just what if the unexpected occurs, right? What if they're working and the worker next to them slips and falls and breaks his leg? What do I need to do, right? I can't just keep going in my procedure while this man's laying next to me with a broken leg. I need to do things, right? You have to train them on that up front, because if you wait till it actually happens, their response is going to be based on their knowledge and their experience, and that may not be what you want. So you pre-train that, so when those events happen, you have provided them a guide path for response, and it's one that you want them to follow so that you get a consistent positive result for those events. And this has to be done before they happen, not after. When you can use not applicable on a step, remember, a procedure writer put all these steps in there because he thinks you need to do them. So letting your end user just say, no, I don't want to do that, that's really a bad decision, and never should be done by itself. So we always tell you, you got to have at least 2 people, and we would say one of those needs to be a supervisor. So if he doesn't want to do it, he needs to talk to a supervisor, said, I don't want to do this step, and here's why. And the supervisor has that opportunity to correct that, or say, yep, I agree, and we will mark it NA. But that way you have good human performance. You have 2 people independently thinking about this step, and they make a decision together on where to go. We talked about placekeeping. When you get interrupted, you forget where you are. And some of our checklists and procedures and power plants are pretty long. So placekeeping is really important. One of the things that's really interesting, I ask people in meetings and conferences, how long on average for a person to get back to their original thought pattern after they've been interrupted, which is really surprising to a lot of people. So you think maybe 5 minutes, maybe it's 12 minutes, right? Well, maybe it's 15, or maybe it's 3 minutes. And if you look from the University of California, they've done studies, it's actually 23 minutes. So if you interrupt someone, for them to get their mind back to where they were before you bothered them or interrupted them, it's 23 minutes on average. So that's a big impact to someone performing a procedure. So try not to interrupt them when they're doing procedures, and make sure those people are doing placekeeping, because they're going to forget when they come back if they're not. All this stuff is in a procedure writing guide that research we've done across the industry. Hazardous energy control, we do a lot of assessments and plan evaluations on that. This is where we hang tags or lock some tags to prevent energy from starting when people are doing servicing on equipment. And here's some error traps that we see on that. If you look at the tag they hung, it's got a name of the equipment. You look at the sheet they're using to hang it from, it's got a different name. And if you look at the equipment label actually on the equipment, it doesn't match any of those. So again, we're setting our end user up for failure. This is a huge latent organizational weakness. Labeling, our equipment lists, and things like that not matching causes a lot of events. Definitely in this case with hazardous energy control, you can kill people very easily making mistakes like this. We talked about operator rounds, things that we see are different that cause human performance errors. There's no labeling on instruments. You want the operators to take readings, but you don't tell them which instrument. If you look at these, you would have to look up when you look closely, you will see that on the instrument, someone has written with a marker, number 1 or number 3 down here at the lower right on that gauge. The upper gauge is number 2, and they had to do that on their own so they could figure out what readings they need to take, because there's no labels on this equipment. What about sensory checks? If you look around in the general area here, are there leaks or water leaks? Are there oil leaks? Is the lighting good? That's not mentioned on their operator rounds. The general area conditions. Look at the piping. Do they have an insulation where, they've done a repair? They put the insulation back. How does your operator know what to do with a bad reading? Right? Have you trained them? What do you want them to do? Do you want them to call a control room? Do you want to notify a system engineer? Do you do the same readings when the unit shut down? Steven's talking about in India, when plants start cycling, what are you going to do when the equipment shut down? Do you want the guy to do time on these rounds when the equipment's off? Probably not. Are they required? Do they change when I go into seasonal layup? If the plant's off for a period of time, do I still need to do the same readings? I doubt seriously that you do. And then when I finish the readings, what I do with the round sheets. If they're electronic, that's usually a better thing, but if they're manual still and they're using paper, what do you want us to do with them? Then we talk about DCS alarms. This is where we let technology get in advance of humans. And we did a really poor job with DCS. We still do. One of the first things that you got to worry about is we all have to agree what an alarm is. And we have a definition as pretty much an industry standard. If you look at IEEE, they use the same definition. But it's a signal to the operator that informs him an event is occurred or is occurring that requires an operator to take action. I'll just jump to the endpoint. But if it doesn't require an operator to do something, it is not an alarm. It needs to go somewhere else. When we look at alarm management, how many alarms can a human actually handle a day? It's about 150 to 300. If your alarm count for the day is higher than that, your operator can't see any more than that. It's just physically impossible for a human. Here's an alarm count when we did an alarm management study with the utility. Notice where it is, somewhere above 6,000 on sometimes, but it never drops below 1,000. Your plant is less safe with DCS than it was with the old bench board enunciators because the alarm count is so high. It's physically impossible for a human to respond to that many alarms. So when you get past that alarm count, your operator head basically explodes, not so much, but he goes into a performance mode called cognitive load shedding. And what that means is the operator, based on his training, his experience, he's going to pick what he thinks is the most important alarm, and that's what he's going to respond to. That may be good, that may be bad, but that's the best he can do. And that's because we set him up with too many alarms. So we've got to manage those. We've got a couple of documents that help with that. It's a continuing program. We see it all the time. And it takes a lot of effort to get your alarms under control because they're digital alarms now and you can add them so easily. And one of the other things we want to talk about is alarm graphics. This colors and data is bad. It's not good for an operator to be monitoring a plant, and we see these a lot, right? Data is non-information, and that's what you see on this screen a lot, just digital data points. So it requires a lot of training, a lot of inherent knowledge, and it's just too much. I mean, if you look at a DCS, there's usually 40 to 50 screens, and expecting an operator to memorize every one of these things and know what the acceptable range is pretty bad for us as an industry. It's not possible for a human. And then if you look at the other part of that is the color. Color, we'll talk about that in just a minute, really quickly. So what kind of data and format does your end user need? This is my dog. He was sick one day, but you know, the vet gives me something like this. It says, here's his blood test. Well, that doesn't help me any. That's a bunch of data, but I'm not a veterinarian, so it doesn't help me. It would be better if he gave me this, right? Now I know I can look at the blood test and I know the range. So I got an idea if my dog is healthy or not based off his blood. But I can make that even better and make it more visual. So when you get a higher degree of situational awareness, and even better is if I put those ranges there and instantaneously I can see if I'm good or bad. Sir? Sorry. The screens, if you look at the screens, this is a pulverizer screen, 4 graphics. We recommend what we call grayscale, and here's a same screen put into what we call grayscale. And the reason I talk about this is the color draws your eyes. There's so much color on this screen, you can't, nothing can come in that you would see very readily. If you use grayscale and any color appears, it pops up really quickly to your eyes.
No problem.
If you look at the cold flows on the pulverizer on this side, this is what we were talking about, data. Here's all those values, and you can kind of do it on the grayscale screen. You can just glance at it and instantaneously see issues. You don't have to be an expert at that plant, but you can look at it and have an idea of how that's deviating on some of those pulverizers. So wrapping up, we have some technology for human performance. We're moving over to, a lot of plants are moving over to tablets and pads out in the plant, but we we're also working on hands-free devices. To the right there, the helmet you see is called, it's a head-mounted tablet. We're working on augmented reality procedures, QR code scanning, remote subject matter expert. We're working on that. Operator rounds and a CMMS, putting all of those things on this mobile device so that your operator is better equipped to work in the field. Here's an operator at one of the plants we were working at where he's up on a ladder and he's using the head-mounted tablet. It's voice controlled, so he has hands are free. He has a hand so he can get up there, and he's looking at a plant tag.
No.
It has the description, the plant equipment ID on it, but on the back side it has a QR code, and he can scan that with his head-mounted tablet to verify he's on the right component and where the position should be. Appreciate you guys' time. I know it's right at 20 minutes, and I want to leave time for my fellow people. So thank you very much.
Thank you,
I'll
sir.
look to the end for questions.
Thank you so much, sir. So, I mean, you have been you have dealt a very important part of the process. Technology is one part, but people is even more important than the technology, and they only manage the technology. And various things which you have stated is the procedures, the operator round, the DCS alarms, and the tracking graphics, and empowering the people with the tools so that they can, their job is, done with more efficiency and ease. So these are the issues which you have mentioned, and I think they are very important to be followed in our procedures. Thank you very much.
So now going to the next speaker, I think.
Yes, sir. Now, I would like to invite Mr. Jeong Kim and Mr. Justin Thibault on leveraging the low-code business intelligence tools for the fleet reliability and cost optimization. As you know that the low-code technologies can create intelligent solutions with minimum use of code and can generate, store, and analyze data as well as integrate them the third-party software. So it's going to be very important. Please, sir.
All right. Can I get the ball, please?
Sure. Mr. Mehul, can you organize? Yeah.
Jimmy is going to. Yeah, yeah.
Okay, okay.
All right. Thank you very much.
So
all right. Hello, everyone. My name is John Kim with EPRI, Program 224, which is Integrated Asset Management. And we also have my coworker, or I should say my teammate, who's the senior technical leader for our program. We probably need to have that person on mute. I think it'll continue on if not. All right.
I was running.
Okay. Anyway, we'll move on. Okay, so today we're going to talk about business intelligence tools. So Dwayne Coffey just talked about human performance, the O&M best practices, and you've noticed there was a lot of talk about data information. So what do we do with them, right? Well, first I want to define what BI tool really is. In terms of asset management, equipment reliability, which is what my program researches. So to us, a business intelligence tool enables, excuse me, almost anyone within an organization to readily observe a set of organized and structured information to make intelligent decisions on how to manage the asset on a daily and long-term basis. And I really want to emphasize the organized and structured part of this business intelligence tool, and I'll talk about that here in a second. But in the next few slides, what I wanted to do is kind of go over some scenarios and business cases and some of the research we've done around those business cases where we're leveraging BI tools. And then my teammate Justin Thibault will go deeper into and show a demo on some of the tools that we're using here at EPRI. So example number one. So this is an example where we're looking at the fleet-wide asset management and, or I should say the process of which, right? So focus on, how we do maintenance, how we do equipment reliability, or I should say support equipment reliability from also from an operational standpoint. So, when we perform these type of management across the fleet, first of all, we need to know what each plant is doing, right? How are they performing? You've heard of the old phrase, if you can't measure, you can't improve, right? So, or manage. So where you're looking at the right-hand side is on the top there, it's color-coded metrics of each of the plants and the regions. And then the left side, you can't really see it, but I kind of blew it up on the farther left side there with the examples of the key elements that's being measured. So things like unplanned downtime, PMs and your predictive maintenance programs, cost management, what's your program, process look like, your training management, RCA, and so on and so forth. So these are some of the examples of key elements that you would take a look at for your fleet in terms of asset management. And then if you look over to your lower right of your screen, it's kind of a blown up version or zoomed in version of what you see up top. So offhand you can see that the BI tool has created some trending, potentially some statistical insights, and then now you can make some informative decisions. But also want to note that obviously what you see in the lower right corner is not going to, you're not going to be able to make a decision right away. It's all over the place. So part of, if you remember the definition, right, part of the intelligence tool is to make sure that we have an organized and structured information, right? If you don't have that, we're not going to make an intelligent decision. So that's going to be a lot of, and Justin, when he does his demonstration, I think can kind of show you what I'm talking about there. So example number 2. So let's say we've done the assessment. We know what the fleet-wide looks like in terms of the maintenance and reliability management. Now we want to figure out how to improve. So we need to develop strategies around that. And this is just an example of, okay, we've done these assessments, let's say across 10 plants. And can we break it down to different tiers, right? So maybe a third of the plant is in phase 1, a third is in phase 2, a third is in phase 3. In order to get there, we've got to obviously take a look at what's showing in the business intelligence tools. So if you look at phase 1, things like, maybe it'll tell us that, hey, on your computer maintenance management system or your enterprise asset management system, it'll show that your work management process might be weak, right? And to that point, your scheduling and planning, there might be some going on, but not to the extent that you're actually getting things done on time. Your spare parts management metrics, maybe there's none that exist, and so on and so forth. And then as you look into phase 2, things are starting to get a little better, right? And so the point here is that we're having to look at the BI tool, but we also are leveraging that to develop strategies in order to move the part of the fleet from phase 1 to phase 2. And then, of course, obviously phase 3 as well. So as you can see, it is definitely a powerful tool and is a prerequisite if you want to look at a fleet-wide asset management improvement or transformation. So the last example I'm going to show you is the benchmarking and statistical insights. So Justin is going to expand a bit more on this and show you some real life examples, which will be very exciting to see. But this is actually one of the things that we're currently working on in my program, and it's a very important project for us because folks are looking at EPRI for industry knowledge. And so what we're doing is we're compiling some of the asset management metrics across the industry, and then we want to benchmark it, right? Who's doing the best in managing CMMS? Who's doing the best in managing spare parts inventory, and also who's executing their work orders the best, and so on and so forth. So those are the benchmarking that they'll be powerful for the industry, because that will set the standards, and that would again measure so that they can improve, so that the whole industry can improve. And then the statistical insights. So one example that we're currently working on is we're compiling millions of work order data that were received from the other utility companies who are our members. And we're just not staring at it at the screen and saying, wow. What we're doing is we're data mining it, we're organizing it, and then performing some advanced statistics to look at things like probability of failure of certain important or critical equipment. So, there's a lot of obviously machine learning and other analytics that uses physical modeling and SME information to build probability or likelihood of failures of components. But we want to take that a step further and look at use some of these BI tools to gain some statistical, real empirical data and get some statistical insights in the next 5 years or 10 years. So something that would definitely help out with capital expenditure spending, but also management of outages. All right, so I'm going to turn now over to Justin Thibault.
Thanks, John. I appreciate that. While they're moving over here, I would ask that if you are not speaking, please make a point of muting your microphone or using the mute function in WebEx. So John had mentioned that, hey, we want to talk about a real world example. So the question gets to be is, why is it that EPRI got themselves involved in business intelligence tools in the first place? Well, the story goes to the United States and our power market. As you know, we have a different power mix here in the United States because of some different resources, different market. And one of the things is that hydraulic fracturing or fracking become very prevalent, and that lowered the domestic cost of natural gas. Well, of course, nuclear has been a important source of baseload power, just because of the fact that the fuel cost was so low, but the O&M cost has grown over time in order to keep those units both safe and reliable. The nuclear industry developed something called Delivering the Nuclear Promise, or as it's known as DNP. And the idea there was to lower the cost of O&M significantly over a 3-year period. EPRI played a part in that through something called value-based maintenance. And one of the key tools in value-based maintenance was leveraging a business intelligence tool collectively to analyze work order data and look for trends. So what we did was that we asked for work order data from over 10 years from each utility. That wound up being over 15 million work orders from dozens of sites. And what happened was that we were able to accelerate the maintenance basis optimization. Now, what I'm going to do is I'm actually going to drop the link to this report in the chat. So if you're watching in the chat, you can look at that link. That report there is a success story that looked into Exelon's use of work order data visualization, and they were looking at $80 million US in savings by 2025 by just looking at their 10 most costly equipment types and reducing the non-critical maintenance on them. So this is something where they were able to not have to go through some sort of very involved data science exercise. They were able to use a very straightforward tool. So very quickly, what does this tool do? I'm going to show you it in a few minutes, but what I'd like to do is just go over the fundamentals. What we were able to do is bring these work orders in and then standardize the dashboard views, right? So that way people aren't spending a lot of time working on the UI. They're just bringing it to EPRI, and then we go in and bring in the different dashboard views, and then also looking over a 10-year period. Most of what we're doing is not very sophisticated data science. What we are doing is we're looking at the fundamentals. So through filtering, both through direct filtering and also drilling down, we're allowing those in the business to do a lot of the work that we're hearing that data scientists are doing. And that's really important, because when you bring these data science tools from the domain of the data scientist to the people in the business, you leverage that domain expertise. And the results we've seen is, first off, you're able to assess fleet program effectiveness. All right, so people who understand what is going on in those programs, what the cultures are, that sort of thing, they're also able to see what the downstream effects of those are. The next thing you're able to do, you're able to benchmark facilities, and I'm going to show you that in just a moment. In that you're able to look at facilities of similar types and compare their performance. Now that's overall insights, but you're able to dig into data. One thing we find, and you may find this at a lot of your facilities, is that different departments have what we call like hours dumps, or they have somewhere where people commonly charge, and looking over a long period of time, you're able to find those patterns without having to use any sophisticated machine learning or advanced data analytics techniques. Also, you identify your data barriers. Talk to any data scientist, and they'll tell you they spend most of their time dealing with data quality issues, data wrangling, data cleansing. Through using business intelligence tools, those data barriers become very prevalent before you have to go give this to the data scientist. So what you're able to do by utilizing data science, by utilizing business intelligence tools upstream, is you're making your data scientist more effective. So what we did on the generation sector is that we took this infrastructure that Nuclear developed, and we put together a pilot. So this pilot involved about 10 different members. We looked at, we had 262 facilities, 3 different companies. You see the various different types of fuel types there. And total value of the work orders we have there is $10.7 billion. And we were able to give some very quick insights to these members for without having to utilize a lot of resources. And I'm going to actually show you very quickly a demonstration of that. So we have a utility here, and they have multiple regions. They're a large utility here in the United States. Of course, we've anonymized this, so we're not going to be using plant names. We'll be using plant numbers. And we're looking over a 6-year period here in one region. And we notice that you have these top 3 facilities. So what I can do is very quickly is I can highlight those. All right, so I'm not having to go in and do the data wrangling at the command line. I'm able to use this graphical interface, and I noticed that there's a large there's these facilities that make up actually still most of these costs that I had for this overall region. Now, what I know about these facilities is that they tend to be a little bit older. Stephen Storm talked before about keeping the boilers up and running, and that you have a lot of uncertainty in your costs. So we know that capital expenses come up a lot. And maybe I want to optimize a little bit more of what Dwayne was talking about with the O&M. So what I can do is very quickly click on these capital costs and then come in here and exclude them. Now, what I'm going to find is that when I'm just looking mainly at my operational costs, again, OpEx versus CapEx, I noticed that facility 48 is a very strong performer. Now, I've got a lot of analysis tabs here that I can go take a look at. We don't have time to do that. But one of the things I want to do is hone in on maybe a cost that I can control. So I'm going to come here to the work order type description, right? And I still see that I'm spending a lot in what's known as corrective maintenance, but I can control PMs. So I want to see if there's a difference in the PM programs. Again, like I mentioned, same company, same region, almost the same plant type. So I shouldn't see a lot of variation in my PMs. So when I come back here to facilities, I notice it does tighten up again. But what I notice is that facility 48 is still the lowest cost facility, right? Now, if I were just looking at one number, I notice that they do spend the most money in labor. So if you were doing just a spot analysis or something, you may miss that. And that's the importance of using business intelligence tools. And like Dwayne had mentioned before, really thinking about the human factors that are involved there and what a business analyst is going to go look at, because a business analyst can see that even though facility 48 had the lowest overall cost, it also had the highest labor cost, right? So I also know from before that for my for when I take out capital expenses and I'm just looking at OpEx, facility 48 is the best performer, right? So I'm getting all these insights. I want to figure out what's going on. So what I'm going to do here is I'm going to come into cost trend, right? And I can see here that there's different variations. And if I want to dig in a little bit deeper, what I can do is I can actually send this to Excel, right? So I can go from this tool that looks very broadly to something I'm a little more familiar with. Now, just to save some time, I actually did break down each one of these facilities. Remember before we had facility 9, facility 48, and facility 69, right? If you look here, facility 48 isn't always the lowest cost facility when you look year to year, but what you can tell is it actually has the lowest variation. So what you know about that is that particular program is not only providing lower OpEx, total OpEx results, but it actually has the lowest variation of the cost when it comes to preventative maintenance spend. And that's one thing I can control. So when I'm looking at benchmarking facilities just inside of my own company, I might go look at that particular facility and find out what it is that they're doing that maybe other plants aren't doing. What type of behaviors do they have? You're able to hone in on that. Again, this whole time I haven't gone in and done any sort of very sophisticated machine learning analysis, that sort of thing. Now, there's different parts of the institute that does that. Again, I've taken that 20% of the effort and gotten 80% of the results. So what does this mean to you? Well, we're taking this from a supplemental this year and we're moving it over into the base program, which the 224, which is the program that Jung Kim manages. So as you see here, this is the overall member process. What we do is, just starting on the left, we agree on our goals. We move into what's known as an onboarding discussion. So we find that group of the team is going to be working on inside of our WO data environment, and then we work with them to build out we start with a custom. With a standard view, and then maybe do a little bit of customization based on the insights that they're looking for. So how long does the whole dashboard development process take? Well, we get the initial data from the member. In about 2 weeks, we do what's known as a data profile. If there's any changes we have to make to that data, maybe it isn't organized in a way that's going to give us the insights or anything like that, then we just go back to the member. What we found is that we don't have to cycle as much as we thought with a lot of our generation members. Then from there, it takes about a month to, once you're in the queue, we've got a lot of work going on. to go through there, and then we go and develop a dashboard, right? And we have what's known as a member enablement meeting where we have those insights. So this is something that we're going to be expanding. Like Jung said, we're going to be going beyond just benchmarking inside of utilities to benchmarking at an industry level. Very excited about doing that this year. As we make this transition, we're looking at different data agreements, that sort of thing to go bring people in. But we've been actively working with members also to provide not only individual insights, but looking into strategies to providing industry level insights. That being said, I'm going to hand this back over to Jung.
Thank you, Mr. Justin. Yeah, it was a very value-based presentation on the value-based maintenance, and the tools which you have described here are really the need of the day, because the processes and the operations are becoming more and more complex, and they need to be handled with certain AI-based tools and machine learning programs and some advanced interventions in terms of diagnostics and process optimization. So we'll have the questions subsequent to this. And now we have one more presentation on this is that is on the online monitoring for the intelligent generation. And on this, I would like to invite Dr. Prayag Parekh.
Thank you. So, good afternoon. My name is Prayag Parekh, and I
Good afternoon.
Power Electric Power Research Institute's Monitoring and Advanced Data Analytics program. Today's presentation is about one of the EPRI products called Continuous Online Monitoring Guidebook. So, what is continuous online monitoring? Within the context of this guidebook, the continuous online monitoring is permanently installed sensors providing continuous or intermittent measurements that can help us with either keeping the reliability at the same level as when performing a manual PM task, preventative maintenance task, or improving the reliability compared to the manual preventative maintenance task. So this guidebook has 8 volumes. Each volume discusses various aspects of continuous online monitoring. With the manual preventative maintenance task, most of the utilities spend more time collecting the data than actually analyzing it. The installation of continuous online monitoring sensors can change that, and time saved in collecting the data can be used for analyzing the data. In a way, we have improved sensor technology now, improved communication technologies that makes it possible for us to implement continuous online monitoring type of sensors, right? So this is just a summary level of information for all of the volumes. So on the left-hand side, it shows some of the values derived from continuous online monitoring. And on the right-hand side, it shows various volumes that addresses those aspects of continuous online monitoring. So, continuous online monitoring enables centralized analysis center. So centralized analysis center can monitor health of multiple units of a fleet from centralized location. COLM. So continuous online monitoring guidebook volume 2, 3, 4, and 5 addresses questions related to the development of business case for centralized analysis center, operations and management of those center, staffing requirement, as well as how to sustain funding for that center, right? COLM can also enable advanced pattern recognition type of software and some of the advanced analytical type of software as well. Continuous online monitoring guidebook 106 discusses some of the current state of diagnostic, as well as it provides some of the example technology providers that are out there which can perform some of the diagnostic using advanced analytical methods. Volume 7 discusses example APR model using existing sensors as well as example APR models that we can use with additional parameters derived from the additional sensors that we install using continuous online monitoring equipment specific guidebooks. And I'm going to talk about that volume 7. Moving to the next line, continuous online monitoring supports equipment health insight, and volume 7 provides practical guide to select effective sensors that can help us detect some of the fault. Volume 7 also provides basis for eliminating some of the manual preventative maintenance tasks. And finally, volume 8 provides current state of visualization tool available for power industry and some of the examples of the tools that are available by technology providers. So at the bottom, that is the deliverable. That is one of the product, and it's linked. So this is the number of that particular deliverable, continuous online monitoring guidebook. So I'm going to go through various volumes and some of the things that that are discussed in those volumes. Volume 2 of the guidebook goes through the discussion regarding business case development for centralized analysis center. What would be the estimated cost for that? What would be the potential benefit out of the continuous online monitoring? And how to communicate this value to leadership. This type of aspects are kind of discussed in volume 2. Volume 3 of the CLM guidebook goes through the program implementation and change management plan. How to develop charter for the continuous online monitoring program? What are the various governing documents that we need to create? A program organization, who would have what role in this program? One of the very important aspects of any digital transformation is involvement of information technology and cybersecurity team member at the very beginning stage of the project. We have to include IT and cybersecurity team member at very beginning. If we fail to do so, the project will either stall or make it canceled. Just because for any digital transformation type of project, we will require the help. We will know what sensor we want to install, which data we need to need for monitoring and diagnostic. What would be the frequency of the data? Where do we want it? All those kind of information. But what we don't know is that what is the bandwidth of our network? How do we make sure that we transfer that data from one place to another place securely? So all of that will include IT and cybersecurity team members' power. Another lesson learned from the experience is that senior management support is needed for any type of digital transformation type of project. Volume 4 of the continuous online monitoring guidebook goes through the staffing requirement. It also talks about how to measure benefit of the center and communicate those benefits to the senior leadership. And in doing so, consequently, how can we sustain the funding for the center? Right? So those are kind of information discussed in the volume 4 of the continuous online monitoring guidebook. Volume 5 is focused on infrastructure selection, various equipment selection, technology, software selection process, how to go through that process of selecting those kind of equipment and software that we need for this center. So this is just showing how limited number of sensors provide limited visibility into the equipment anomaly, as shown on the left-hand side of this slide. And then right-hand side of the picture shows how installation of additional sensors can improve visibility into the equipment fault. Right. So volume 7 of the continuous online monitoring guidebook provides that guidance on selection of additional sensor for various power plant assets. So the goal of volume 7, equipment-specific continuous online monitoring quick guide, is to reduce the number of manual preventative maintenance tasks using continuous online monitoring type of sensor. So how do we decide on which sensors to use, right? So we work with subject matter experts from EPRI as well as power industry, and also use EPRI's preventative maintenance database, PMBD. Basically, this PMBD database, preventative maintenance based database, has information regarding various failure location, degradation mechanism, degradation influence, that kind of information. We go line by line for each failure mode and ask subject matter experts various questions related to the sensor selection. This sensor information for each failure mode is based on subject matter experts' knowledge and experience with that type of failure mode and that type of sensor. And there are going to be there are some instances where we don't have any sensor, right? So at that time, we just mark that particular failure mode as not applicable for the continuous online monitoring, just because we don't have a sensor for that. But that is also one of the important information that we derive, because if the particular failure modes or set of failure modes that are critical for that particular type of asset, and we don't have sensor for that, then it provides us information regarding the sensor gap itself. So the equipment specific guides are generally 8 to 10 pages long, and we intentionally kept it that way so it's easy to digest. One of the important things of this equipment specific guide is related to the ideal sensor layout, as shown on this slide here. This particular page shows information regarding general step-up transformer. It shows various sensors that can be installed on GSU, the table here on the left-hand side. The approximate location of various sensors are shown using bubble on the picture of the transformer on the right top right-hand side. And then the bar chart at the bottom generally show highest value sensor to lowest value sensor. So that information helps us in identifying which sensor we want to install first. If we have limited budget, which sensor would be most valuable to install on that particular type of asset. So that type of guidance is provided in continuous online monitoring quick guide volume 7. These are all the quick guides that we have published so far, and all of these quick guides are available in volume 7 together. And if you want some specific type of equipment quick guide, you can look at one of these deliverables as well. All right. So I kind of skipped. I talked about volume 2, 3, 4, 5, but I kind of skipped volume 6 and went on to volume 7, just because volume 6 and 8 are related to some of the technologies that we as power industry don't have long experience with. So this volume 6 and 8 don't really discuss best practices as with the other volumes. So volume 2, 3, 4, 5 goes through various aspects of the continuous online monitoring. It talks about the best practices, but volume 6 and 8, just because we don't have enough experience with those particular type of new technologies, we don't talk about the best practices at this time. Volume 6 of the continuous online monitoring guidebook discusses current state of the diagnostics as well as some of the example of advanced tools that are available out there. Again, we don't have much experience with that, but those are the tools that are available to us if we want to taste them, explore those tools. Volume 8 goes through the discussion regarding visualization tool. So current state of the tools for equipment, unit, fleet, visualization. It also discusses some of the visualization requirement based on the industry discussion. And again, similar to volume 6, it also provides some information regarding some of the advanced tools that are available out there. So with that, I think I kind of finished on time. Any questions?
Yeah, thank you, Dr. Parekh. It has been a very useful information regarding your this continuous online monitoring manual. And I think the concepts which you have discussed in them in it are very much applicable to the industry today. And hopefully the participants would like to go into the more details of this to incorporate these concepts in their power plants. Mr. Mahul, do we have any questions listed?
No, sir. We don't have any questions listed right now. But
Okay.
maybe we may receive few questions at a later time. So
Okay.
if we receive any questions, we can share it with the speakers, and whenever they get time, they can answer that. As of now, we don't have any questions.
Okay. Can I ask Dr. Parekh that this manual which you have created for the continuous online monitoring, now how this can go to the interested power plants?
So are we? So the question is regarding the access or?
Yeah, access and implementation support.
Okay, so the access is available via EPRI.com and available via our program, which is program 228, monitoring and advanced data analytics program, as well as John King's program, program 224. And it is also available to purchase. And as far as implementation goes, that's completely different project, but in certain ways we can certainly support that. Mike, if you want to comment on that. But yeah, certainly, I mean, certain part of the implementation we can support.
Okay, thank you. Now on the loop technologies, I would like to ask Mr. Thaimbold that on this, what are your, that is again through the membership support, or it is off the shelf product available to the members?
So the question, as I understand it, is this only available to the members?
Yeah.
Yeah, that is true. Originally, we had a smaller collaborative, about 10 members who funded a very specific project called the Equipment Reliability Analytics Collaborative. And now it's going to move to a broader collaborative, which is Jung's program, which is about 30 companies. And within each one of those members, we ask that there is a select group of people who will be working with the dashboard, because we have, because of the software we're using, it has a limited number of licenses. The important takeaway here is that even though we are making this member access only, there's two things going on. One, we're able to provide both individual insights to members and then also take those collective insights and incorporate them into the system. The second part is by collecting this data, we're getting a broader understanding of program performance throughout the industry, and we'll be reporting that back through our R&D results.
Okay, thank you.
Thank you.
And one question I would like to ask to Mr. Stephen. Yeah. On this boiler flexible operation, what are the different measurements that you have specifically recommended with reference to the various stresses and strains developed in the boiler, and specifically to the headers and the risers? So and if it is to be on the specific zones, can you just throw a little light on that?
Pankaj. So in program 223, it's a relatively new program where we integrated heat rate and generation flexibility. And because flexibility is so complex and it impacts not only the boiler components, but turbine and other major components, we have a number of tools that we've been developing and to be able to drive and prioritize what solutions are most important. So it might be thermocouples on superheat headers, or it might be on the reheat. So we do a lot of collaboration and integrated support with program 214, which is boiler life and availability. And so there's publications like the others have talked about that are available on those resources that give some of the background on where those types of thermocouples should be located, what thermal wells, what other sensors and technologies are being integrated to be able to manage those components. But the most important thing is to understand what your modes of operations are. So in 2020, through NTPC, we developed a high-level flexibility assessment tool to really look at 600 different parameters across 10 different templates to try to understand where those gaps are and where the issues are at a site-specific plant, because that might vary from a unit that's 5 years old versus one that's 30 years old. So it depends on the specific unit.
Right, sir. Thank you so much.
Pankaj sir, we have one question actually from a participant.
Yeah. Please ask.
There's a question on what could be the boiler efficiency variation at 60% load compared to 100% load. I mean, when you are reducing the load to, let's say, less than 60%, what could be the variation in the boiler efficiencies?
Yeah, so typically you see a significant degradation in boiler efficiency when you drop down to lower loads because you operate with a higher excess O2 set point. The other factor is that you've got steam turbine cycle thermal inefficiencies that increase your firing rate that can also impose issues with heat rate degradation. So, and then you have also the issue of fixed amounts of parasitic power. And so in our program on the heat rate side, we've got some tools and control loop optimization, supplemental projects, and advanced techniques for doing audits of things like auxiliary power and understanding what those best practices are to be able to manage and optimize heat rate across the load range. But it's not untypical in India to see 100, 150 kcal per kilowatt hour heat rate degradation as you drop down to low load because of the oil consumption or the dry gas losses, and especially if you have issues with combustion and you're overfiring the boiler because maybe other issues with turbine cycle degradation or seals or whatnot. So again, it's going to depend on the site-specific unit. There are things that you can do with sliding pressures and operations to improve low load heat rate and efficiency. But that's going to be determined after you do an assessment and evaluation of what your current capabilities are versus your design. I hope that answers the question.
Yeah, thank you.
Mehul, any other questions?
No, sir. You can conclude and we can move on to the next session, sir. We have only one presentation in the next session,
Okay.
so
Okay.
we can complete this.
So I would like to thank all the eminent speakers from Electric Power Research Institute, and there has been, very enlightening, information on the various subjects discussed here. And I would also like to, appreciate the human factor, which has been talked out in such a scientific details as to how, it's not just the individual's own ability, but also, how we empower him to become able. So that's a very good, realization, and a thing which is to be appreciated by all, to be incorporated into the system. And the application of these low code technologies, and more emphasis on the continuous online monitoring system, because with the complexity of the operations of the plant, it is very difficult to depend on the offline optimization measurements, and optimization with the help of offline measurements. So that's a very important concept which has been discussed here, and I think all these information will be very useful. And as you have mentioned, that how this can be made access by being the member or whatever way it is, so that can be discussed with you in detail, whosoever is interested. Thank you so much. With this, we conclude the session. Mehul, over to you.
Thank you, sir. Thank you all the participants. Request you to join the next session. We have one last speaker for the day. Then we move on to tomorrow's session. Thank you, everyone. Please join us tomorrow as well, and for the next session as well. Thank you, sir. Thank you, Mr. Storm. Thank you, Mr. Parik, Mr. Justin, Mr. Coffee. Thank you very much. Mr. Michael, yeah. Thank you, everyone.
Take
Thank
care.
you, sir.
Bye.
Bye.